helpful. So, because instead of having such a big chunk of material. So Thursday, we're hoping for clear skies. If we can see the moon at least a little, that's what we're going to do over there on the hill. If we can't see the moon, then I've got a couple other things in mind that we're going to meet actually in room 302, which is right next door. So, so of course, 9:30, the campus is closed then. So I talked with the maintenance, and they're going to make, I think the arrangements is this door will be open. So you have to come in this door if you're wanting to do that. Remember, you need to get 2 labs done by October 20th or something like that, 22nd. I gave it to you the first day we met. So 2 labs need to be done by then. The other day, I kind of mentioned the whole moon journal, so that's a possibility if you want to go ahead and start that. Remember, the moon journal is something you can do on your own, and let me know if you have any questions about reading through it, what you need to turn in. You look at the lab for 2 weeks. And I tried to say that for that lab, if you're doing the moon journal and say it's like cloudy, okay, then you say for that day it's cloudy. But otherwise, you should be able to find the moon. That's easier said than done sometimes. So actually, I posted under Twitter a good link for when does the moon rise and when does it set. If you're doing your moon journal, I would do that. I would suggest that. Okay. All right. So let's pick up where we left off. Now, there's a chance that we get through this lecture material and I show you just a little bit of the movie I wanted to show you. The movie I wanted to show you, in case we don't get to it, actually is Dr. Brian Cox video. He's British, but this series actually kind of reminds me of the Universe series a little bit. The Universe series has some great material. It just didn't have what I wanted to talk about the formation of the solar system, but Brian does. So yay for Brian. So this is a figure from your textbook. I like it, and it's chock full of information. So of course you see each row is going to be a solar system object. That we've kind of already talked about. We'll be talking more about it. But one of the things we need to discuss today, the formation of the solar system, is kind of this division. I'll go ahead and draw it here. This division right here, okay, between Mars and Jupiter. Of course, Mars is our last terrestrial planet, and Jupiter is our first gaseous planet. And we're going to talk about why that is. After the last gaseous planet, of course, we have that rascal Pluto, okay? And Eris, actually, you may not recognize the name, but Eris is the object that the grad student found beyond Pluto's orbit that is also orbiting the sun. And so Eris temporarily was our, 10th planet? Eris temporarily was our 10th planet? And like, no, dude, we cannot do that, okay? So basically, Pluto and Eris are kind of similar. You see how close they are to the sun. This next one actually says how big they are and what their density is. I'll go ahead and draw that line in again. Okay, so here we go. Mars and Jupiter. There's the line. Okay, notice that Jupiter, they don't call them gas giants for nothing. Okay, they're definitely larger than the gaseous planets, are larger than the terrestrial planets. The other thing is density. Okay, density is basically kind of how, if something is dense, they're not dumb, right? It's dense. It means it's like stuff is atoms are crammed together, okay? So the terrestrial planets are dense and the Jovian planets are fluffy, okay? The gaseous planets are fluffy. So actually you can see the density of the terrestrial planets, the density of the Jovian planets. The density of water, the symbol for density is that. So the density for water actually is 1.0. Okay, so that's kind of fun to think that actually Saturn would float in a bathtub of water. Is that not cool or what? It's less dense. Okay. So then the next actually says how long does it take to complete one orbit about the sun, and the other one is how long does it take to rotate on its axis, and then is its axis of rotation tilted. So I'll just kind of draw your attention to a few. Remember, Kepler, one of Kepler's laws says that the farther out the planet is from the sun, the slower it moves in its orbit. Not only is its orbit larger, but it moves slower, okay, and that's a gravity thing. So actually, if we go ahead and pick on Neptune, okay, It takes Neptune, Earth takes 365 days to complete one orbit about the sun. It takes Neptune 165 years, okay, 165 years to go around the sun once. It takes Pluto 248 years to complete one trek around the sun, okay. One other thing to kind of point out, and it'll probably come up when we talk about Mars, but Mars actually, it spins on its axis once every 24 hours or so, rotates on its axis, and its axis of rotation is tilted, not entirely dissimilar from Earth's. So Earth's axis is tilted 23.5 degrees, Mars' axis is tilted 25.2 degrees. Okay, so they're a little bit sister like that. But they say that actually Venus is more like Earth and Mars is like Earth. How hot is this? The surface of the planet is the next column. Okay, and the last column says what is the planet made of? Does it have moons and does it have rings? So again, I go ahead and kind of put this distinction between Mars and Jupiter. Okay, one of the things that may come up as we looked at the planets a little bit, but we look at the planets even more in Unit 3 in here. But actually, if you look at moons, right, Earth has one awesome moon, one outstanding moon, okay, and Mars has two moons. They're kind of ugly, okay, but then look at all these moons. You're like, really? Okay, check out all those moons. Okay, the other thing with regard to the gas giants is notice that they all have rings, and they all have kind of faint bands. So I think that is an outstanding sort of figure. Before I realized your textbook had it, actually I was going online looking for one just like that. Okay. So this thing we need to talk about is called the solar nebula theory. And remember, theories, if they've come through the scientific method process, theories are not just guesses. Theories need to be consistent with observations. And you need to, based upon a theory, be able to predict things. I have a slide coming up that basically shows that our solar system with the sun and the planets, it's happening other places, okay? That's to say that other stars are actually in their kind of infancy. Other stars are just being born, and they also kind of have planets around them. And we kind of see stars or planetary systems in different phases of their birth. So what observations do we need to account for in the solar nebula theory? They're kind of summarized down here. When we talked about the Earth, I said if you look down at the North Pole of the Earth, I said it's all about counterclockwise. That's to say that the Earth orbits the sun counterclockwise and the Earth spins on its axis counterclockwise, right? So all planets orbit counterclockwise. Now, most planets spin on their axes counterclockwise too. The two exceptions are Venus and Uranus. So we'll talk about why those exceptions occur. Most moons also orbit their planet counterclockwise. The moon, our moon, capital M, orbits the Earth counterclockwise. Okay? So we need to be able to explain those patterns of motion with this solar nebula theory. The other thing is we need to explain those two broad categories of planets we've been talking about. The terrestrial planets, the inner ones, and then the gaseous planets, the outer ones. Like, really? How did that happen, right? So here's actually kind of a compare and contrast table that your author's done. Talking about, of course, the terrestrial planets would be the four inner planets. And then the Jovian planets, those are the gaseous planets. Gaseous planets. Makes you want to giggle, right? Me too. So a lot of this we've already talked about. So why is that? Also, in our nebular theory, we need to recognize that we definitely still have some other things in our solar system that aren't planets. We have a whole chapter devoted to asteroids and comets coming up in Unit 3. So here is a picture of an asteroid. Some asteroids get named. So this is the asteroid called Eros. Okay. And then here is a picture of a comet in action. So one of the things that to know is that actually they differ by where they're located and what they're composed of. So, for instance, asteroids, okay, most asteroids are in the asteroid belt that is between the last terrestrial and the first Jovian planet. Most asteroids are there. And most comets are actually located out beyond Pluto's orbit. We said, I think we talked in Unit 1 where actually there's this thing called the Kuiper Belt, which is in the plane of the ecliptic, and then there's the Oort cloud. So that's where your comets are. So what exceptions do we need to go ahead and absorb into our nebular theory? When our nebular theory is done theorizing, it needs to make sense of these. Okay. So, for instance, the two planets that rotate backwards, I'll go ahead and put them up here by name, and we'll talk about them coming up. But poor Venus rotates backwards, as does Uranus. And it's not a full backwards, well, one is, but Uranus isn't really a full backwards, but Venus really is. Okay? And some moons rotate and orbit their planet backwards. I'm going to go ahead and lead you to it. Mars, the two moons that Mars has, not only are they ugly, but they're kind of weird in that sense too. And then it's an anomaly, and I think I've used that word before, that actually Earth has such a large moon, which hopefully we'll get to see tomorrow. Okay, so Earth's moon is totally crazy large compared to what it really should be. So, the nebular theory. Okay, so we've talked about the term nebula in here before. So I kind of said, think of nebula is if they put something in the telescope for you to view, and they're like, oh, it's a nebula. You're like, oh, so I'm looking at a cloud of atoms, cloud of dust, particles. Okay, that's a nebula. So it's the solar nebula. It's the nebular theory begins with a nebula called the solar nebula. So there's basically a chunk of gas out there that was left by another star, okay, or more than one star, that actually turned into our solar system. It's called the solar nebula. And we talked about galactic recycling in here before, the fact that stars live their lives and they make heavier and heavier elements, and then as they die, they give that material back. That's how we got our solar nebula that has heavy elements, okay, from stars living their lives like that. Speaking of galactic recycling, down here actually is the little picture of galactic recycling we looked at before. I almost think it's a misnomer because to me it almost looks like star recycling instead of galaxy recycling. So star recycling, just to kind of remind you how that works, okay, I'll put a number 1 here, okay. Actually, as I'm drawing a number 1 up there, that is a star that's not turned on yet. Basically, that is a nebula there. And we're going to talk about actually kind of how our star went through this phase a little bit. But a star is being born right there. And it shoots out oftentimes jets of energy, okay? And actually it has a plane of the ecliptic. Can you almost kind of see the plane of the ecliptic there? Kind of right angles to the jets of energy it's shooting out. So at some point our star turns on. That would be number 2. Right here it becomes a full-fledged star. Okay, and then number 3 is trying to show you its death. Okay, so 2 is life, 1 is pre-life, 2 is life, and 3 is death. So that's galactic recycling. And so it's this matter then actually that can be used by another star. Okay, galactic recycling, stellar recycling. Okay, so back to our solar system. How did this whole thing work? So kind of from left to right at the bottom, you see the different stages of our solar system's life. This is the solar nebula, this kind of fuzzy looking thing, okay? So it's much larger, the solar nebula is much larger than our solar system is today. That's a player, okay? Solar nebula is very big. Our solar system is significantly smaller than that. The solar nebula had a bit of rotation to it. The solar nebula, but it was just kind of like, just slowly, solar nebula, just slowly counterclockwise. So when we talk about stars being born in a nebula, this nebula in and of itself is not going to birth any stars. It needs something outside the nebula to get it going. So we think maybe like a star out here blew up in a what we call a supernova event. It sends shock waves in all directions, including the direction of our solar system. It kind of begins the little thing in the center that's going to become the sun. It's kind of like making the sun and making the planets are kind of like making a snowball out of snow. Basically, you kind of have to get it going. Okay, and that's what that initial event would have been. Okay, so you kind of see from left to right, it got much smaller. It had some rotation. It gained the nugget in the center. It had some rotation, and it got smaller. So now one of the things we covered in Chapter 4 on motion and gravity was this idea of energy. When it was large, it had lots of potential energy, and as it contracted, it had less potential energy. So that energy can't be lost, and it was actually converted from potential energy, gravitational potential energy, to kinetic energy, specifically kinetic energy of thermal energy. It got hot, basically. Okay, that's all to say the darn thing got hot. Now, for any, I'll point over here. This, to me, doesn't quite look like it's a full-fledged star in the center. I don't think our sun has turned on right there. But for any star to do its thing, for any star to shine, okay, it needs to have extremely hot conditions in its core and dense conditions in its core. And that's being created over time. Okay, so this is the birth of our star, the birth of our solar system. This is how the other stars are born too. Okay, so we talked about the conservation of angular momentum, okay, and that's to say it's the best one is the skater with her arms out and the skater with her arms in, okay? So with her arms out, the radius is big, but the velocity is low, okay? Remember, this is the little equation, actually. It's on our review session. Okay, so angular momentum, choose a better color. Angular mo, okay, is equal to the velocity that it's spinning times the mass, m, times the radius. This is my r. I know my v's and my r's kind of look alike, okay? But the thing we talked about is that as the skater decreases her radius, she increases her velocity. And that's exactly what happened here. So velocity is the spinning part. So basically, if it was just barely moving before, okay, gravity kicks in, it becomes smaller, it becomes hotter, and it spins faster and faster. So there's a consequence of something spinning faster and faster. It kind of flattens out like a pancake. Okay, so that's kind of where our plane of the ecliptic came from. Faster and faster. It's just kind of what things do. Particles interact, they kind of find the common center. So, kind of in a nutshell from left to right, that is our solar system being born. So I mentioned that your theory needs to be consistent. You need to be able to predict things from your theory. And we would predict to see this nebular theory happening to other stars, and we do. So what you're looking at here are those little jets of energy here on the left one. Okay, right here, these are the jets of energy kind of squirting out. Okay, so actually the star is here, and this right here, kind of how I've drawn the red, that actually is kind of going to be your plane where your planets are going to be formed. There's where the pancake is. Okay. So that's pretty cool. So here's where we get to kind of start talking about the whole two types of planets things. It's very different being on planet Earth. You're like, oh my gosh, I could never go to Mars. It's totally different. Well, it's not entirely different. Okay, so Mars and Earth and Mercury and Venus, at least you could stand on the darn things. Okay, Jupiter, Saturn, Uranus, and Neptune. We're going to talk in Unit 3 where the only thing you can stand on basically is if you fall through the gas and hit this kind of rocky nugget at the center of those gaseous planets, which would not be a good thing. So the thing is, I like this slide. Okay. this really reminds me of making a snowball, like I said. So to orient yourself, this actually is our budding solar system. The thing in the center is our ever getting warmer, gonna be sun sort of thing, okay? This white line is important. It's called the frost line. This white line actually would be between Mars and Jupiter, okay? That white line is right between the terrestrial and the gaseous planets. It's the frost line. So if you think of frost line, think of what frost is basically you go out in the morning and on your blades of grass, you basically have water, solid water. That's what frost is, okay? So the frost line is kind of trying to describe where something goes from a gas to a solid. Frost line. Gas, water vapor in the air goes to a solid on your blades of grass. You figure basically as you get farther from the sun, you're going to be getting cooler, right? Why does frost form? Because it's cooler, right? Over the course of the night. So the thing is over here at the left, we have actually 4 different things that when our solar nebula was going to ultimately become our solar system, what was in that darn nebula? There's the 4 things, and they are listed in order of what was most abundant and what was least abundant. So over here, I'm going to put a 1 next to hydrogen and helium gas, a 2 next to hydrogen compounds, a 3 next to rock, and a 4 next to metal. The reason I'm doing that is how abundant were they? And I like what your author's done. Basically, the size of the square over there is the relative amount that was in our solar nebula that was that. Okay? Now, if I were to ask you just walking around Earth, that sort of thing, you'd probably say, I know I definitely, even though I haven't had a chemistry class, I know that I'm interacting with metals and rocky material. But look at what the abundance was in our original solar nebula. 0.4 and 0.2%. Okay? Is it a player on Earth? Yes. So here's the deal then, what is also important. If you look for rock and metals will actually condense. Now condense means go from a gas to a liquid, okay? So rocks will actually go from a gas, you're like, gaseous rock? I'm like, yeah, gas to a liquid, okay? At a significantly higher temperature, okay, than these other things. So that's to say, even though it was hot here on the inside of the frost line, it was cool enough for these things to begin to condense. Okay, so I'm going to put condense over there. Okay, so here's the deal. If you go from the hot side of the frost line to the cool side of the frost line, then actually you can begin condensing hydrogen compounds, which are present in 1.4%, relatively speaking, in our solar nebula. Okay, so this can begin condensing when you're on the cool side of the frost line. So let's look at what those hydrogen compounds are. We talked about compounds. Remember, compounds are atoms of 2 different elements that are running together. So here we have the formula for water, H2O. Okay, we can have that go ahead and begin condensing. Ammonia, I skipped methane. Methane is CH4 and ammonia is NH3. So actually we're going to see those compounds in our gaseous planets. All right. So this whole kind of snowball, if you take a snowball, your goal is to make a snowman. So you take a little bit of snow, pack it together, and then you start rolling it through the snow to make it bigger and bigger and bigger. That actually, in astronomy, in this whole planet making, I would call that accretion. Okay, you're making it bigger and bigger and bigger. Now, it's different from a snowball versus a planet. Basically, the reason that little pieces kind of came together to make not a full-fledged planet, but you see the term up here, planetesimal at first, okay? The reason we kind of got these little chunks, okay, these little chunks right here, is gravity and kind of electrostatic attraction. So we have this stuff kind of on a frisbee, okay, because of its rotation. And basically, within a given lane, you have material coming together, which is going to make a planet. Actually, kind of that little channel of matter that accretes into form a planet kind of reminds me of whenever you finish rolling your snowball, you look behind you and there's like this cleared lane, right? Okay. Remember the criteria that Pluto failed to be a planet? He didn't clear his lane of debris. So that's all something to think about. Okay. So anyway, kind of from left to right, we see the formation of our solar system. We have lots of crumblies and then fewer crumblies. That middle one I would call, those would be the planetismals. I didn't bring it in the semester, but I've even heard sometimes them called planetoid. Okay, but these would be the planetismals. Okay, and then of course these are the planets. And we call that accretion. They got bigger. Notice that actually this slide is kind of limited to the 4 terrestrial planets. We just have Mercury, Venus, Earth, and Mars up there. And let's see, I can't remember how long this takes. I've read it. Say 100,000 years or something like that. It's a while. Because we definitely have, I mean, it's all going on at once because we figure they're getting larger. The sun is maybe taking the material, I don't know how much larger it's getting, but basically taking that material, gravity's working on it to become even more dense, even hotter in its core, so it can begin nuclear fusion. And then we have, on the other side of the frost line, we have the gaseous planets. Okay? So the gaseous planets are kind of similar, but you figure they are on the cooler side of the frost line, so they can also pick up. They get the metals, okay. They get the rock, but they also get those the ices like H2O ice, methane ice, and ammonia ice. Okay. And then the deal is basically when they get large enough, they get massive enough, the gases, which are most abundant in the solar nebula, can go ahead and start sticking to them because of gravity. So once they get large enough, gravity can kick in and keep those gases associated with the planet or the wannabe planet. Okay. So that's kind of it. It's kind of accretion, and then, well, it's very similar. But we also have gravity kicking in to gather that gas that never will condense. If you look back at the table where I had 1, 2, 3, 4, kind of the 4 different things that were in our solar nebula, the temperature at which hydrogen and helium condense, I think it's not on there. Like if you look back at that little table, what's it say? No, not that table. This table. I can't read it, but condensation. I think it's, yeah. I think it says it doesn't condense. You're fine. So then the bottom of the slide actually talks about something else with regard to the gas giants. Remember how many moons they have? Oh my gosh, they are so piggy with those moons. We're going to see Jupiter, Saturn, Uranus, and Neptune definitely have like over 30 moons each, I want to say. I have to look, but over 30 moons. So the way they got their moons actually shown in this inset right here. The way you read this inset is basically you have the whole sun is getting bigger, right? So here's the sun in the center, okay? And then out here, actually, on the other side of the frost line is, let's pick Jupiter. Let's call that Jupiter. Jumping Jupiter, okay? So out there where Jupiter is, basically it forms its own kind of mini little disk of material that you can go ahead and have accretion happen around these swirling clouds of Jupiter. Okay, so basically you can have little moons form out there with those swirls. That's how they got their moon systems. Okay. All right. So there are a couple dates in astronomy that you need to know. One of them is how old the universe is, and we're kind of putting it at 13.5 to 14 billion with a B years old, our universe. Our solar system is about 4.6 billion, again with a B years old. Okay, so those are kind of the two dates. So what happened about 4.6 billion years ago is that the sun basically, and I've been talking about it here this morning, the sun, in the center of the sun, it became hot enough and dense enough to begin nuclear fusion. Okay, all stars shine because the energy they create via nuclear fusion. And if you kind of think of, not the drink, like fusion the drink, but if you kind of think of fusion, basically it is actually slamming two atoms together and making something heavier, which kind of makes sense because we get the heavier elements, but it's creating a lot of energy. Now, when the sun turned on, and ever since, it creates this kind of positive pressure called solar wind. So right now the sun is not only shining, but it also has this, it's literally a positive pressure going from in all directions. So the thing that the solar wind did was to actually clear the area. So remember a little bit ago I said, oh, I know that sun hadn't turned on yet. Basically, when the sun turns on, anything that had a relative size to it, like the dust and that sort of thing, it all got cleared away. So what was the solar nebula basically went downstream. In the meantime, we definitely had our 8 planets, our 4 rocky planets and our 4 Jovian planets. In addition to that, we had some of the miscellaneous stuff we talked about earlier. The asteroids, definitely have a belt of asteroids between Mars and Jupiter. And then we also had kind of some miscellaneous comets that are generally located in the Kuiper Belt and the Oort cloud. So that's kind of in a nutshell. This actually, from top to bottom, are the phases that we've talked about. Okay, the last one being the sun turning on. If you compare these two, the last two scenarios, you definitely see that the gas is cleared out. So let's kind of look at those, let's look at some of our current evidence as to kind of if this makes sense. So the whole asteroid and comet thing, it kind of makes sense. The things that didn't really come together to become a planet, like I said, kind of leftovers, that explains those two things. We see on various objects in our solar system, we see a variety of cratering. Of course, there are craters on the moon, okay, that basically anytime an object is cratered like the moon, something hit it and left a little impact, okay, kind of being shown here. The fact that stuff was cratered, and one of the things that we know is that actually our solar system went through a period of time when there were a lot of miscellaneous stuff being flying around that could cause this cratering, a period of heavy bombardment. So the best, within the realm of what we know, explanation of why we have the water that we have actually has to be related to this kind of period where it was chaotic in our solar system, where comets could actually cross the frost line and come hit the terrestrial planets. Okay, so comets actually hitting Earth and the planets was how we got our water. Because you figure water early on, water would not condense because it was too hot there. Okay? So it was deposits from comets that gave us our water. So up at the top, if you would change this word, I would greatly appreciate it. No, we're okay. It's on the next slide. Don't change this word. Okay, so what about the whole moon thing? Well, we said Mars has a couple of moons that go backwards, okay? And actually, here's the pictures of Mars moons. Don't they look different than our moon? I'm just saying, right? Okay, so meet Phobos and Deimos. So they orbit Mars clockwise instead of counterclockwise. And they look ugly. And it's most likely that they were just kind of in the wrong spot or the right spot, the wrong time or the right time. And they became under the gravitational influence of Mars and just never left. They became inserted in orbit. Okay, so that kind of explains those moons. The other exception we need to explain is why Earth has just a crazy large moon. for being a terrestrial planet. And the best theory out there is actually something called collision ejection. So you kind of see it going on here, kind of from left to right. Collision occurs. This impactor is sometimes called THEA, T-H-E-A. So an impactor about the size of the planet Mars, when there was still chaos in our solar system, hit the Earth. Earth is still a little bit ooey-gooey at that point. Okay, the Earth actually ejected some of its material, okay, around the Earth, and that stuff came together to make a moon. So it's kind of, let me show you down there. So the way you look at this basically is you need to kind of do a slash right there. Collision, okay, and ejection. And this is the material that actually came together to make the moon. And here's the Earth in there. So a pretty good drawing. And there's the impactor going on about its business. Okay. Collision ejection. Now, this explains how the, let's see, how do I say this? It explains a number of things. It explains how the moon came into be, just in general, but it also explains our tilt. Okay, and we're tilted 23.5 degrees relative to being perpendicular. Now, evidence that actually this is the case is actually the moon is made from Earth stuff. Okay, we get very similar when the Earth was what we say kind of differentiating, kind of has its lighter basaltic rock up here. That actually is the material that became the moon. So our highlands, our mountains are very similar to the composition of the moon. Kind of the light stuff of Earth actually. Light, it's Earth light. Okay. The other thing is that actually, along those lines, I guess the dating of the moon rocks, but I guess that's kind of similar. That's coming up, dating of the moon rocks. This is the one I need you to change, where it says planets orbiting the sun the wrong way. Oh my gosh, I can't believe I wrote that. It should be planets rotating on their axis the wrong way. Rotating on axis. Oops. Okay, so planets rotating on their axis, spinning on their axis wrong. Okay, the two planets I told you were Venus and Uranus. So let's take a look at Venus first. Venus is so awesome. So it's all about counterclockwise. So we're like, okay, Venus, you're supposed to spin counterclockwise. But actually, the same kind of situation that gave us our tilt, actually, it got hit, but it actually swung all the way around. Okay? So now, actually, when you look at Venus's north pole, it's rotating clockwise. Okay? If you were to look at that table I showed you a little bit ago, comparing all the planets, the column where it says the tilt of Venus's axis, actually, it's a 180. So that's kind of how that goes. It's just crazy. Okay, so it rotates clockwise. Venus was hit very hard. Uranus wasn't hit as hard. Uranus was, do you remember the picture of Uranus we looked at? Actually, Uranus looks like its axis of rotation is lying in the plane of the ecliptic. Okay, so its actual tilt is about 90. I think it's 89. Okay, so this backward spinning we actually call retrograde rotation. Oops, I guess I should have put those up there. So two planets that spin or rotate backwards are Venus and Uranus. All right. Last couple of slides. So I mentioned the 4.6 billion years ago our sun turned on and kind of cleared the gas debris anyway. Okay. Well, how do we know that? Well, a number of ways, but we are going to I think in Unit 3 in here, we're going to talk more about asteroids and comets. But in Unit 3 in here, we're going to talk about meteor showers. I mentioned that because meteor showers actually are the cool visible thing, okay? But after a meteor shower, if you're lucky, if a rock has actually made it through Earth's atmosphere, that's what creates meteor showers, you'll go and you'll pick it up and that's a meteorite, Okay, so meteorite is the space rock that survived passing through Earth's atmosphere. So we can date meteorites, which are really space rocks, okay? And when we date space rocks, okay, we come up with about 4.6 billion years old. So you might be like, well, how can we date something that long, that old? Remember I told you carbon-14 dating the other day? Carbon-14 dating only works if something's been alive. You're like, okay, this meteorite has not been alive. Well, we can use another form of dating. Basically, we know the rate at which the element potassium, like special K potassium, right? Potassium over time will actually break apart and form argon. So you see potassium and argon. Okay, it's a radioactive decay process. It takes a while, okay, but it's very well understood the dynamics of that element transitioning into the other element, potassium and argon. So basically what you do is you see how much potassium you have left and how much argon you formed to get a sense of date. Okay, that's how that works. So here we go. The results are in. Okay, when we talk about the Earth, you're probably going to buy into this, the fact that the Earth's surface, we walk around on, actually it continues to go through changes. That's to say there are volcanoes that kind of resurface it, right, with the lava, and it has subduction zones, and so basically our surface isn't as old as our solar system because it's been geologically active. So our oldest features go about, our oldest rocks on the Earth, about 4 billion years. Okay. Moon rocks, about 4.4 billion years. So actually this kind of makes sense if you consider the whole collision ejection theory of how the moon was formed. Okay, 4.4 billion years. Okay. And then I get the 4.6, actually, it's down here, it says 4.5, but I get the 4.6 from 4.55 billion years, okay? And again, it goes back to these meteorites, which are space rocks. Space rocks associated with our solar system being that old. And I think that's it. So instead of showing you any of the movie, because we only have 6 minutes, what I'd like to do is I think I'm going to be able to find a link on on YouTube for this Brian Cox flick. If I don't, then I guess you'll just have to go with what I said. So that's it for today, and I'm going to head that way, and like at noon then, I said after class, but it'll probably be more like noon. So if you're going to want to do the study session, noon would be it. Okay, room 512. That's it.